Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our conceptual lecture 3, which introduces us to some very important parallelization fundamentals. So this really means we want to understand a little bit more about basically how we crunch down a big problem into smaller pieces and then solving these smaller pieces with parallel computing in order to solve the whole and the bigger piece. There are some contexts which refers to basically domain decomposition, a word which is very important basically in simulation sciences in HPC, something that is not obvious to you, but we see how that materializes when we see the first part and the second part today. But before we dive into the material of lecture 3, let us review what we had the last time. And the last time was really about a practical lecture building on all the conceptual aspects we had in the lecture 2 on the message passing interface. You could say it's basically the de facto standard in parallel computing, a kind of language really that has stand the test of time, so to speak. You have very many applications today in parallel computing, leveraging HPC systems that really are built on the MPI standard. Sometimes this is combined with OpenMP. If you remember the earlier lectures, MPI is more for distributed memory computing, while then basically OpenMP, which is then shared memory computing. So when you combine this, it's something called hybrid computing often, which is quite substantial today also in many applications. But we started basically in lecture 2.1 really to have the first real MPI application. Real in the sense that we before just used the scheduler with C applications, but we have also seen that basically a C application can be very easily extended, that you see perhaps here with the simple ping pong by introducing the header and then having an init and the finalize of MPI, which determines then basically the space where we can do parallel computing. And we learned about several different important functions in the parallel lecture. In the practical lecture where we had MPI com size and then MPI com rank here, whereby basically the com size always would say the communicator here in this example, the MPI com world, the basically communicator of all processors asked for from the scheduler. I know how big and how many of these processors are actually in there. And more notably for us, as we have seen, especially in the ping pong here with the red parts, I can use the rank information to really understand who am I in the bigger picture, right? So that means although the same source code, right? Again, I repeat, the same source code that you see here will be executed again and again in parallel. So when you don't use this rank information, they will all execute exactly the same logic. Hence, in many applications, like in our very trivial example the last time with ping and pong here, executed from the other rank, this alluding to different application logic that will be executed by different processors. And this is a good example, MPI send and receive, that you had in this ping pong example for MPI point-to-point communication. You see that here again, a little bit illustrative. Because we have distributed memory, you see that here the process has some memory and the processor has some memory, but it just cannot, as a processor here, access this memory. So I cannot have and read this data item. I can only read my own data item, which is 80. If I want to have some new data, I need to send this from the other processor, and that's where the message passing comes into play. Now, this is a bit more conceptual. The real world example would be rather looking a little bit more elaborate, but not so complicated. You would say, in order that process A is really sending something over the wire, firstly, we need to have some out buffer, which would be the data here. In our example, this was, let's say, the ping here, right, with the X. And then basically it goes over the wire, but as we also know, really again and again iterated on, the other processor need to be ready to receive, right? You see this very brilliantly in the ping pong example. We send, and the other rank is ready to receive. And this is just the ping. So it ends up in the system buffer and then basically in the application data that are basically reserved here as the in message you see here. to receive the out message from the other core or processor, that is very crucial. Hence, needless to say, that was just the ping, right? We reverse the roles if we then think about that the second one is doing the pong message of preparing the out message with 1 char and send it back to 0, which means, in other words, 0 also need to be ready to receive. I need to stop now there. I think we have been going through this particular example now many times, and I think it's getting boring for all of you. So I think you probably understand that. They always think about the ball analogy that you have in real life. If you want to pass someone a ball, make sure the other is ready to receive. Another part of this very practical lecture was also to understand the power of collectives. We had said in many ways, by the example of broadcast, for instance, you could think about iterating with a for loop through all these different processes. You say, I want to send with a for MPI send receive this data item to this processor, this data item to that processor, and so on and so on. So this could be very elaborate in a for loop. Think about maybe here when you have 10 processors, and we learned that this is not really necessary. So instead, by not really using a for loop, we could do broadcast, define a communicator that includes all of these processors I want to have information sent to, and then basically just have a one line, right? Instead of having very elaborated for loops, determine the processors, having a send receive construct, depending on different ranks and so on and so on. What's much more simpler here is doing a broadcast. And in the same way, the collectives work for, let's say, giving data out from one processor to another. We have basically also quickly learned that basically you can do a scatter of an array here that you see, a gather of an array here from different processors. And then even with the reduce operation here, you can basically include their several operators. So this is also something what you will do in your assignment. So basically, you will get to know MPI much more in the first assignment. And with this is what's also important to show you a couple of other examples in the practical lecture, how to work with a scheduler. And one of the things was basically having this S control, show job ID, really understand what you ask for. When you ask the scheduler for a node is different than basically asking the scheduler for a core or a processor. Hence, we had this minus capital N and minus N, small modifications in a job script, but of course have a real big impact then when you schedule the job. Equally, we had also discussed that essentially there's one very important part where we had the analogy of the sailing boat actually crashing against a wall. And this is an established term in HPC when we say the job or the application in HPC was running against the wall. And this referred to this idea of the wall time. So you basically specify how long you ask the resources from the scheduler. This is a loaded question. Obviously, when you start programming, you maybe don't really have an idea how long your application is actually running. So often it's a bit like experimenting with this wall time. Of course, on the other hand, you should also not use 3 hours, 4 hours when your job just takes 10 minutes. Because we have also learned that this wall time is used by the scheduler to schedule your job. And of course, if you are much more closer to the reality, chances are that your job is maybe backfilled, that you early executed, and usually all users want to have their application as early as possible computed. That is not so easy. That's why we have the scheduler. I think, again, we iterated on the idea that basically you share the HPC system with many different users that have all different types of jobs and running at the same time at the HPC machine. That's why we need the scheduler in order to manage all of this. And that's why also the wall time is quite crucial to understand how all of these applications are essentially scheduled. But let us come now a little bit to the next parallelization fundamentals. In a way, some of these things we already touched upon when we think about MPI, but more from a technical perspective to really start with the practical topic very early to get your first assignment going. The parallelization fundamentals are now looking a little bit more on the conceptual ideas. What are typical strategies to basically perform a parallelization approach? This could be meaning different things, and we will talk about it. It is related to domain decomposition, but what happens with basically, if you crunch down a domain and you want to exchange data, you need to have some space for this data. So you introduce something called halo and ghost layers in simulation sciences and data sciences. So we will talk a little bit about this, and then some other parallelization aspects, which are really established terms like SPMD versus MPMD, single program, multiple data, multiple program, and multiple data. And with this, you basically get a little bit an idea of the overall ideas of parallelism. Then the second part of this lecture is much more thinking about some established terms again, but also a little bit of theory. But don't worry, the theory is not so complicated. It actually alludes more to things like what is a speed up, what means weak scaling, what means strong scaling. There are certain laws in HPC, like the Amdahl's law or Gustafson's law, we will understand in the second part of this lecture. So sort of, we're really thinking this lecture is now complementing the MPI lecture, while MPI was really about the programming directly. Basically, lecture 3 would be much more sort of thinking, how can I now approach a problem and really try to make it in parallel happen. And with this, we basically really learn certain established aspects of domain decomposition. When you want to have something simulated, which we call the domain, we want to simulate, let's be a wind farm, or basically the water where we set the wave propagation, this would be the domain. And when we want to solve this in parallel, we want to decompose that domain. That's something what you will learn today. Then, of course, we enter the domain of more and more complex aspects of parallel programming. You will see the domain decomposition is not at all obvious, although many of you would probably think, let's do all blocky, let's do a Cartesian everywhere and do everything nice and shiny at the same, let's say, bunch of bricks, sort of crunching the big problem in smaller pieces. We will see there are many different approaches to domain decomposition, and for a certain reason, called load balancing, for instance. And with this, you again come to the notion of different abstractions, really, of parallel computing on various levels, whereby in MPI, we have been really on abstraction with the, basically message passing, which was not really involving very many network protocol aspects, but rather focusing on the data at hand and the message exchange. Here in this lecture, we rather think about the abstraction of the whole domain, of the whole problem, and then see how we can break this into smaller pieces. So another level, if you want, and then you decide, let's do it with MPI, let's do it with OpenMP, let's do it with both, which is the next step then in the game. So with this, we really come more and more to practical aspects again for programming HPC applications. And this is, of course, something which you should really know after this lecture. So let's dive into common strategies for parallelization. And some of them seem to be very obvious. I can imagine many of you know. And also, when you think about parallel computing, we have to revise a short statement, which is very important now. And this is basically what you see here in a cooperative way, right? So this is something which is important, in a cooperative way. I just don't do parallel computing for fun. Basically, the problem is large, big, and so I need to basically crunch it down in smaller pieces, doing it in parallel and in a cooperative way. That means, in other words, when you have this HPC application running here, the processor should not just have their own lifetime, basically work on their own. We want to basically solve something in a cooperative way, which means probably some message exchanges. And this also, of course, alludes to the overall problem. So what is the problem I really want to solve? Also, when we talk about parallel computing, you remember parallel can be many things. Here we're talking about a multi-core CPU processor that we have introduced. Inherently, this is already parallel because this is a multi-core chip with different cores. You have seen this also in Newton, right? We have 12 cores basically, and 2 times basically 2 chips. So we had this 24 cores available, and then this is already enabling us parallel computing. But that's not where we want to stop, right? We want to involve more processors. We want to basically then, for a big problem, use a couple of nodes and many of these different processors. Hence, when you now think about a typical multi-core CPU, and when you want to, let's say, have a first simple parallel computing example, if you will, why you should use parallel computing, you can imagine this here a little bit. You have an array maybe of 16 elements, and you just want to have the maximum value, right? So immediately you would say, okay, that's pretty simple. So when I want to crunch this down into 4s, let's assume we have 4 cores available. It's very simple. Everybody gets 4, basically, that you see in this next level here. So every CPU and cores basically get a certain part of this array and would basically compute the maximum locally. Hence, there should be also someone doing then afterwards the maximum globally from all of this. But immediately it comes to the idea that you can solve this now in parallel. Instead of, basically computing the maximum from all of these 16 elements, you basically can probably get a speed up of just crunching this big problem, which is a big toy problem really here to get the first understanding, into smaller pieces, doing the local basically result and then joining it at the maximum global result here. So this is what we would call already domain decomposition of sort, right? Of course, it's a data domain here of 16 elements. We have a certain number of cores. It's something to decide. And then basically, compute this. Every core is more or less doing, again, the same work, right? Just on different data. Hence, you would say, again, it's a little bit like SPMD, same problem or same program, multiple data. And this is something what we will later understand. Obviously, you always have to think a little bit more out of the box here, because there's also someone from these 4 cores that actually should do the maximum global. Right? It cannot be that this is flying in the air. So in a way, this trivial approach of saying, well, let's divide this whole work into 4 same pieces is not true, because there needs to be some of these cores which might be rank 0, right? Let's assume this is rank 0, where rank 0 is then responsible for obtaining all the local results first, and then when once obtained, can basically compute the maximum. Or it's core 2, core 3, core 4, it doesn't matter, but some core needs to actually compute this. And this is a little bit, let's say, misleading here, and also that is exactly the points with it, right? Although you would think this parallel problem is very trivial to solve, just 4 different pieces, you will always find some load imbalance, because there might be some core, some special one that takes on the master role. And this is what we could call the master worker paradigm. So these are the workers, but one of the masters responsible for collecting and then giving out the max global. And this is already alluding to the complexity. Although often it looks so simple to create basically a parallel problem application out of it, it's not at all so obvious. And when you come to many cores in GPUs, and we will have a whole lecture 6 around it, where we'll talk much more about this. There we have very specific tensor cores these days available. I leave it as here because we will have also a whole lecture there. So here you have heard there are specific tensor cores that already are very optimized for deep learning. This is something which we will talk about in the upcoming lecture 6 and basically 7 when we talk about more deep learning, and also Reza will later pick up on that. This is a massively parallelism, and the reasoning why this is so massive parallel is that there are many, many hundreds and thousands of processors on a GPU chip. You have seen that in the graphic as well, or in the video. So these chips, however, are not very high single thread performance. So these are, let's say, low performance chips, or medium, you would say, not the ones that you have in the multi-core CPU. Hence, the understanding between many core GPUs and multi-core GPUs is very important. They have quite of different roles. Still, we will also talk here about parallel computing. And needless to say, when we come to lecture 6 and so on, we will also learn that not only tensor cores are basically leveraging parallelism on one chip. Also, we again want to interconnect GPUs doing distributed deep learning, and with this having the power of many different GPU devices available for learning from data. But this is not all directly obvious to you. We have to first learn a little bit about more what is deep learning, why we learn from data, a little bit of machine learning 101 if you want. And then basically we'll see how that really leverages HPC today. And also here's some small parallel decomposition, if you want, domain decomposition of a typical computing, which the CPU can do very nicely, like matrix-matrix multiplication or matrix-vector multiplications you see, for instance, here, right? So you basically see the color coding determines here the more or less domain decomposition, which is just the rule how basically matrix and vectors are actually multiplied, which then referred to the instructions you see here that you can very nicely parallelize because you don't need any other information, right? All the other colors are basically irrelevant. I just need basically this color coding, can solve that on my own on one processor, and the other color on the next, and the other color on the other. And of course, in the end, they fill all up one result vector, which is here this gray fellow. But it's completely done in parallel and landing in the device memory. So as another part of parallel computing, it just demonstrates how GPUs really leverage this. And of course, you can imagine that usually these matrices are not so small and the vectors are not so small, so much more elaborate, and they do this over and over again. By connecting them then with different GPUs, you get even more power. And basically today, you would say the only drawback we have is this GPU chips these days is probably the main memory with the CPU here. You see the CPU always had to basically give something in the main memory via the device memory to the accelerators, to the GPUs. But we talk about GPUs much more in these specific lectures on it. So let's continue a little bit for the idea of parallelization approaches. Here you have a very famous example, numerical weather prediction, NWP. This is a domain which almost all of you have already used indirectly as a user by actually using the weather forecast, which is, of course, in Iceland quite substantial. And there are lots of physical processes that are basically going into these computing elements. And this could be different ways. It could be, of course, a small short-term weather forecast or actually long-term climate prediction, what happens to our Earth. But you see also the characteristics here. You would have some domain decomposition of 3D cells. You see that a little bit elaborated here, where you basically have different grid structures. And what happens within such a grid structure part is already quite elaborate physics. And there are lots of physical formulas that needs to be computed. Often this refers to so-called partial differential equations and solvers that solve a specific problem, often related to laws in physics, like the laws of motion, lots of physics, and fluids is something which you also will learn with Reza actually in the second part of the course much more. There you will basically understand the PDEs as well. Hence here it's pretty obvious we have a ball, which is the Earth more or less, and we basically do the domain decomposition with such a horizontal grid on the one hand, but then of course also the vertical grid, because then we have also the height, which really plays a role here. This is a very famous example, and now you can basically make a little bit an abstraction from that and see the problems we already looked in, which means we have a data parallelism maybe, where you say we had this array and we crunch it into smaller pieces. We had the matrix, where we basically had some matrix vector multiplication in the GPU. These are all different, basically data parallelism domain decomposition. Now, when you want to have certain parts of the Earth, maybe, or the water we discussed with the wave propagation, you could see that the overall domain would look like this. And here's now the idea of the decomposition. right? Again, the decomposition. It doesn't necessarily mean, as you see nicely in this graphic, that every little grid cell is getting one core. You can do this differently and map that differently. You see here we have kind of a blocky character with 8 grid elements, maybe getting to one processor. Hence, here needs to be some communication as well, communication exchanges. And when you then basically more abstract from this, there could be cyclic ones and different ways how you basically crunch this domain into smaller pieces. Another aspect of parallelism might be that you actually have functional parallelism. That basically means that you have the same data, but different processors have different, let's say, functions to perform on that data. You can say when you want to have some part of the Earth may be simulated, you want not to have all of the processors here do the same computing. You can also think that some of the processors doing just the atmospheric model, which is basically interacting with the hydrology model, and then also with the land surface model, just to understand the whole way of precipitation, rain, or basically the flow in the ground. And then, of course, this could maybe interact with the ocean model. So these are different functional decompositions that also are possible, and of course used in parallel applications. Now coming to some term which is important, the SPMD, single program multiple data, where you would say again, from that what we just learned, it basically is related to the domain decomposition. The Earth, there we would basically have the same laws of physics in these different areas, but obviously we are in different parts of the world, so it would be some different data. You know, basically temperature and so on. And then in the MPMD is much more alluding to what we had basically on the lower part of the last slide, where we said maybe the tire is something which a couple of processors are simulating, while the interaction of the flow here, of the airflow of the race car with this kind of race driver is basically perhaps something some other processors are doing. So here we have a functional decomposition, again, from different parts of the race car. And we see in lecture 10 to 15 how we do this also much more in CFD simulations. Now, thinking back, what could be another idea of how we basically now differentiate between data and functional programming? On this scale, we would say a good example is data parallelism. You would have a loop that you can do here from 1 to 1,000. You see that. And you see also basically the interesting way how this is computed is that it's basically independent, again, from each other, from all the runs. It fills essentially the array A, but it's not related to how it's computed. So you have a constant that is here basically always getting up with the index. So we can nicely crunch this into problems and then can obtain a speed up. And this is the first term really getting more and more important here. It's a shared memory example, but it doesn't matter that, of course, when you want to do the loop, and the constant multiplication, you have the second array, then you have a certain t, a certain time. And the reason why we want to do parallel computing is exactly this. We want to crunch it down in smaller pieces to get a time which is smaller than this time I computed here. So in order to do that, hopefully this will be much more faster. And with this, I obtain a speed up with this T2. That's one of the reasons why I want to involve more and more N processors. And when we come to the theory part in the second part of the lecture, we will understand that much, much more. Now, again, another form of data parallelism is now the dimensions we have talked about when we maybe want to have the coast of Iceland here. As an example, we could have a 2D simulation of the coast and basically also simulate how basically here are several phenomena. Maybe this could be, you know, Vic, the Black Beach somewhere, which we want to simulate and understand more notably. But we also see that 2D probably has some limits. So I go for 3D grid of maybe just more understanding the physical phenomena. By going into 3D, you can also imagine we need much more processors. So the number of N processors basically of this grid will play a bigger role now. And I don't have a 2D, I have a 3D, obviously. And for each of the grid cells, think about now the Earth example, I need to compute. So the more fine granular your domain decomposition is, you know, basically we want to simulate the reality. So we go towards the reality, the certain observable. So it's basically lots of physical variables and physical laws, we compute on those, this means also much more computing is happening, right? Because all the physical processes, when you go more into detail and reality, needs to be also computed. So this is quite, I think, a way of good understanding this grid and mesh character. You can do this in different ways. You would say one is a 3D grid where each of the grid item would have a certain data item that is representing then this part of the grid. Could be a multidimensional array having lots of information. Is not necessarily just one data item, obviously. And then you have a sort of blocky representation, right? It looks a little bit like maybe the coast again from Iceland I want to simulate here, looking a little bit like this. However, some elements you also maybe want to have much more smoother simulated. So you see here a so-called lattice, where basically the nodes of the wire then are basically getting here data items. And with this, the whole looks a little bit smoother. But then also, of course, you would have more data items and more computing to be done. And then you see here even more computing if you do basically something we call adaptive mesh refinement. For instance, when you have a mesh which is absolutely not grid-like, but rather, let's say, oriented towards the most computing, where it's getting smaller, and there where less computing is, the bigger cells. This improves also kind of the load balancing, and you can go to an airplane, to a race car. These are very advanced domain decompositions that are possible. So not all of that is today just blocky and grid, although everything suggests in a way crushing down the world in this kind of blocky characters. The realism is that many of the advanced applications have a very advanced domain decomposition, and we will talk about throughout this lecture series. And why you want to do this? Of course, because we want to move towards realistic simulations. Hence, the granularity matters a lot. So think about, you want to have the ocean simulation, the wave propagation we discussed in the wave, or understanding the coast. As I said, it could be maybe here the Wick Black Beach in Iceland, close to Wick basically. The more I go in smaller pieces, more granularity, the more I can understand the complex basically behavior of the whole simulation that I'm doing, because also the ways how I do the kind of physics is more accurate. More and more I will have a much more realistic approach to what is happening. And then think about what I can add. I need to add rainfall, ocean waves, maybe even if there's a ship crash, and then I want to simulate the oil and how it will be distributed. Boats, fishing, birds, you name it, right? The more I add more of these aspects also to the study, this is not only physical laws, it's then also really the interaction with these objects, which of course might be again then physical laws, but not derived from nature. Maybe it's a boat, with an engine, as I was alluding to, going over this. And then we need to compute basically the surroundings very much. And to compute the surroundings and getting information from the surroundings is now one interesting part of this domain decomposition, which is not at all so trivial. So this will be something we were talking about, halo regions and so on. So let's look into a little bit towards this in a moment. Here we see again now an application example, which is the Formula 1. You already know I want to simulate this over time. Also, here's a good example, like the Earth, right? Here I have the interaction with all the materials of this race car with the air coming in. And I want to, of course, optimize this so that the race car is basically, fuel economic cars, or basically have a much more higher speed. Hence, I have to think about now how I do a good parallelization method, how I do the domain decomposition. And then I will exchange this data here between the different parts of the race car. The same is true when I simulate over time. And this is now the important part, often in parallel applications. I want to simulate something over time, right? Like the heat dissipation here you see in a room, perhaps, right? And you basically see with iterative approaches after 50 rounds, 200 rounds, that is often common. And each time step, there's a whole loop over the HPC domain application, and the next loop, and the next loop. And with these loops, I basically compute the physics step by step accurately over time. This will be more obvious when we have the specials also from Razor and the CFD part later. Here you see again some simulations, how that look in. It could be, of course, in 2D and 3D. This is a Jacobi solver, basically, also using here and there stencil methods, quite iterative approaches and known in numerical simulations a lot. And basically, you can come up to different ways how you then crunch this problem into smaller pieces. You see here, simulation with 6 neighboring cells or with 26 neighboring cells. Obviously, this will be probably more accurate, but also need more computing. And these are just examples how you can compute this. Basically, you see here how you basically solve this is not so important. Important is rather that we basically have this heat diffusion equation solved over time. Over time means basically I do a loop, and every time step I need to do something. Of course, I want to have maybe the heat in this particular part of the room. But what this is suggesting, T0 and T1, is important because before I compute at T1, basically the time here in the next time step, the heat in the room, I need the heat of the surrounding neighbors before. Hence, now we talk about message exchanges again. You see that, right? Here, this is now where we're starting. Think about MPI, think about shared memory, that basically in order to compute my heat in this particular tile, I need basically the heat input of the surrounding ones. It's pretty obvious. And then I can solve the equation that you see here. And by iterative going through each of these tiles here with the same approach, exchanging the data first and then computing, this is so-called a stencil code method. So because you basically go with the same idea over all the domain. And then you can show really by iterative doing this through different rounds, you have a very accurate prediction of the heat in the room because you compute the law of physics as it basically should be. Hence, this is loaded. And this is a very important part in parallelization, that basically we need the data of the time step before from surrounding neighbors for computing basically at my time step. And this is to be done with not maybe one physical variable only, it could be many different ones, depending, of course, what you want to compute. This is a two-dimensional Jacobi solver, and I think Razor's example will have quite some elaborate, interesting aspects of this. So let's skip to something which is perhaps more important for more other applications as well. You can imagine with MPI, we had this data buffer where we said, okay, if in order to send the data now to the next processor, I have this data buffer, I do the send, and then someone gets the receive. That's good. That's all basically something I can incorporate. We didn't talk yet about this iterative approach, right? Iterative in the sense of saying, let's assume we have these two processors which take care of different domains. We have the certain problem that when I want to compute here something, let's say the heat in the room at that particular part, I break it into two pieces. I can access the memory, if you remember, just from the other processor. Right? What could be the solution? I do an MPI message exchange before and have something which you see here alluding to, which is rather halo or sometimes also called ghost cells. These are not really existing in the room, right? It's more rather enabling us to exchange the real values that we have basically in the domain next door, and the same actually here, so that when we exchange this data in the time step that is coming, I want to compute the heat, and I can do it because the ghost cells are actually filled with the values from the other processor, right? This is a very established mechanism, sometimes actually more ghost layers or cells. That depends on the application problem, but it's a very important part so that I can compute the physics or whatever it is, basically in my time step here. So that means in a time step before I need the data somehow. And of course, MPI to the rescue. This is something where MPI message exchanges can help. Or basically, if you have shared memory, you can do similar aspects. But of course, with shared memory, usually you can access the memory. Or you basically have a bigger domain where you basically have to fetch, let's say, data first, and you basically do similar approaches. So primarily, this is for MPI for instance, when you have large applications. And we will have some examples out of this. And the way how you crunch now this domain decomposition into smaller pieces is loaded, because you see also here, when you think about communication, that you basically have this world crunched into these 4 equal parts, which is this domain. It seems like it's irrelevant how you basically do this, but you see immediately if you put it into 4 of those, the interactions are much less, right? In terms of updates, but the kind of communication, you have 4 times 8 is 32. And here you have 3 times 16 cells that needs to exchange information of physical properties. So it involves more communication. So it matters really how you do the domain decomposition. And you can go on and go on. I think more and more you get the story. For instance, here in the data parallelism example, you would say you have to cluster something. That's what we already had in several lectures now. So let's say the domain is looking like this. So the processor 1 gets really part of the intensive part of the domain, while the processor 2 gets the remaining part of the intensive part, but also some of these. This is done, of course, to think about really load balancing, because if you would cut it equally, it would be completely load imbalanced, because the processor 2 has almost nothing to do and processor 1 has all the work to cluster and to check all the mechanisms of this clustering algorithms that you see a little bit here called dbscan. Is not so important to you. Important is that here also halo regions are actually used to understand also then, of course, when you have this with a processor in different memory spaces, to understand the location of these points, because they are basically hidden in the other part of the memory. Hence, we have this merge halos and so on also in this cluster algorithm, just as an example that this doesn't need to be just simulation sciences, or also machine learning and data mining algorithms take care of the same approaches. So more about the functional parallelism will be then coming in the CFD, where we have master worker paradigms. I summarized this a little bit, what we had also earlier. Think about that basically, even if the parallel idea is often very simple to parallelize, you would say equal parts, you need always one manager or master, as it is called, to bring the big piece together. And this is, of course, something which we had also in the global max, right? The idea that some masters should have to take care of. The same is basically true for, let's say, larger simulations, and it will be also coming more clear in the CFD parts when we talk about this. Coupling this multi-physics applications with different laws of physics also is basically also happening, and will be also one part of later CFD simulations, even coupling it with deep learning instead of just having numerical laws on physics. So it will be quite interesting examples coming up. And if you have time, I would really recommend you to go to this particular video. As you know, I can't play them anymore here because YouTube doesn't want to have the same video again in the lecture, but the reference is given here. And it's a very nice idea of understanding not only, of course, our volcano here, Eyjafjallajökull, but also basically several other applications in HPC and how they also do some parallelization approaches. So please have a look at this video, and we continue in 10 minutes with our parallelization turn.